Right, so we're looking at equilibrium. My suggestions is not that you do any questions around this, unless you're feeling really confident. Just try and look at some of the interactives, listen to this, watch some of the videos, get your head around what's happening in terms of particles and things flying around. So then when we look further into the maths of it and the graphs and the changing things and doing things with it, you've got a really kind of clear idea in your head of stuff moving. So sometimes we struggle because we can't kind of visualize it. So if you're visualizing balls that are atoms kind of squashing together and changing and swapping and moving around, it's going to be much easier than if you're trying to just really just think in terms of really kind of, I can't even think of the word, just really basically this is what's happening. So you've got to kind of visualize it in some kind of way in your little big brains. Right, so equilibrium. So it's this balancing act that we have, and it's moving on from our very simple, we add this and then we get this. It's about having this balancing act. I don't know if you do it in biology. My biology thing. I would assume you have to do some of it because of gas exchanges and things, but no. Anyway, equilibrium. So we have two types of systems that we're going to look at. We have an open system and closed system. So a system is whatever kind of environment kind of thing is. Again, with all the vocab. So systems. We've got two, open and closed. So our open one, you've got to have your head around some of this stuff before we actually describe equilibrium. So open, we can have both matter and energy being exchanged. So we can have the example they give, bushfires. So when we had the big bushfires, the world is an open system. There was bushfires over there. Things were being burnt. The energy was being released into the environment, into the system, and the energy was being released, and the matter, or that carbon dioxide and the carbon and the water, that was all being released as well. So both of these were being released in our open system because there was no containing it. But our closed system, oh god, my handwriting's getting worse. Right, so the energy is the only thing that's being exchanged in a closed system. The best example I think of this is the space station. So the International Space Station is floating around in space. It's not giving off matter. It's not giving off any particles. It's not giving off anything. The only thing it's going to be releasing is a small amount of energy. So it's going to be giving off energy as it floats through. Yeah. Until they choose to make it open, they might dump something or they might put something out or take something in. But it's a closed system for the majority of the time. And a lot of what we're going to look at is going to be a closed system that you then can make an open system and then close it. And I think if they ask you something about this in terms of the exam, they might give you a kid who does some equilibrium reaction or prac or something. And you have to talk about what kind of system it is, how you can improve it, could we get a perfect closed system in a school setting? Yeah, probably not. But it would be, you can talk about the limitations on that and how you might double up and how you might do this, that, and the other. So that's kind of what we have to think of. And it's going to be a bit of both, but it's mostly kind of a closed system. So we've got our reversible and irreversible reactions. This is what we do in year 8, year 9, I feel I've talked about this a lot before to juniors, but I think this bit's quite simple to get your head around. There is things we can't go back from in chemistry. You burn something, you're not going to get back to your original match or whatever. You've got your carbon now, you've got water vapor being given off, and that's it, you're done. But there are things where we can go back. We can go back. The example they give you is melting ice, which I don't like because it's just a changing of state. But we can go backwards and forwards if something's reversible. So we can go yeah, we can go forwards and then we can go back. So we can think of it as this. So we can go from A and B to make C, but C can also make A and B. This would be really annoying to write out all the time, so we just combine these with our double headed arrow. I completely cannot think. So this is double-headed arrow, backwards and forwards, and it's showing that it's going this way, but it also goes this way. So what we would think of as our products make a reactant, but our reactant can then become a product and make a product. So it kind of can go backwards and forwards both ways. Round, 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 wherever. Alright, so the one we're going to look at through most of the process of example of equilibrium is going to be the Haber process. So Haber, Fritz Haber. This is something kids would have been learning about in chemistry forever. I definitely know I did it. I wonder if Suzanne. I bet Suzanne did it. I bet everyone since the beginning of, since he invented it, has had to learn about it. So it's not explicitly in the study design, but it's the only reason. Like, it's in all the books. It's all over the place. I can't see the expectation of understanding in a lot of depth another process. You need to understand the Haber process as our basis, and then for the SAC, I'm going to give you another industrial process, and you need to apply all your knowledge to this other process. But I'm not going to just throw all like loads of randomness at you. It's going to be, this is a process for making blah. How do we do this and the other? So that's what that's going to look like. And I think that's going to model-ish what they're going to give you in the exam. Because just remembering this stuff, maybe for some of the multiple choice, maybe for a bit of this, that and the other. Right, so Haber, Fritz Haber. German chemist, obviously. Useful in making ammonia. Ammonia, why do we care? Well, there's two things really. Fertilizer, I don't think that's a for fertilizer. And right, fertilizers and explosives. Oh my god, my handwriting's getting worse. Fertilizers and explosives. So fertilizers, I'm going to try zoom so I don't have to write on here. Fertilizers. Why is that useful? Well, fertilizers, I think it's called the Green Revolution or something. Less use of animal waste, or it means we can industrialize our farms much more. So beginning of the 20th century, we have these new fertilizers and we can start making a lot more of our crops. Second one, explosives. So Fritz Haber, German. The Allies block all the ports, block some chemical that I can't remember coming in that they were importing from some of their territories. Now they can make ammonia, they can make their own explosives. They don't have to rely on, I think it's saltpeter or something. They don't have to rely on what they had to rely on previously because they can use this ammonia to make it. What's also going to be used, so my hair dye has ammonia compounds in it. Ammonia is, I'm assuming, it's in cleaning products, it's in probably production of plastics, it's probably in everything, to be honest. And once you've deduced how to make this, it makes, other processes much easier to do. So what did he say we were doing? So he wants to make ammonia. He figured out that if we put some nitrogen gas, so we put into our closed system some nitrogen, some hydrogen, and we get our ammonium. We can use a catalyst. Which is iron. which speeds up the rate of reaction, but it doesn't change the extent. So the rate is how quickly it happens. So how quickly you complete your homework is your rate, but the extent is how much of it you do. So it might take you 2 weeks to complete your homework. That's your rate. The extent is how much of it you do. So I did 10 questions. It took me 2 hours. My friend did the same and it took them 1 hour. Different rates, same extent. So this catalyst doesn't change the amount of ammonia we're making, it just makes it quicker. And if we're doing it quicker, that's good as a chemist because it means we can get through it quicker and get more and more and more pumped out. And we'll look at some of the equations to work that out as we move forward. So we've got this forward and backwards happening at the same time. So we've got these happening and making this, but this is also making these two. And we've got this backwards and forwards and backwards and forwards. And what we call that backwards and forwards is dynamic equilibrium. We've got dynamic equilibrium. Oh, I shouldn't have rubbed that off. Right, so dynamic. Oh, itchy nose, and I just rubbed it. So coronavirus ahoy. So we've got this backwards and forwards in a dynamic state. So we've got this backwards and forwards, and we'd assume from our equation using kind of our, I want to say, old way of thinking, our old stoichiometry, you'd think that you would end up with, you put 1, you put 3, you'd end up with 2 moles, you know, using that normal old arrow way. You put 1 plus 3, we've got 2 moles here, so that's how much we're going to get. But that's not what's going to happen. So we have this backwards and forwards happening, and what we actually end up with is 0.6, 1.8, 0.8. So we're getting a lot less being produced because we've got this backwards and forwards. And it is a dynamic system. It's always constantly going backwards and forwards. So while it looks like we've got this 0.8 moles and you're kind of assuming it's the same, it's not. It's like this swapping around is constantly happening. So it's constantly going backwards and forwards and backwards and forwards and backwards and forwards. This nitrogen goes over here, and then like it's always changing and swapping, but it's just reaching this kind of even level point where we've got these numbers. So that's what I want you to understand. I want you to really get that picture in your head of this stuff happening, the systems, the swapping, before we move on to anything. I will post some questions, but I really want you to get your head around this before we move on, because I think this is going to be one of our sticking points. It's going to be one of the things that we needed to really work on. All right, look after yourselves, be good.